Hello and welcome back. Today's topic is going to be the last thing about taking derivatives that you need to know, and it's called implicit differentiation. Now, before we even get to it, why is it called implicit, right? So far, we've dealt with functions of x, and then it's just all x there, because it's a function of x. In other words, you can do any amount of algebra, and you can eventually isolate y and get things in terms of x, right? But what if you have a function of x and y, right? Something like x squared or xy squared equals 1. That's a valid function. I don't see why not, right? So no matter what you do, you can't fully isolate y. Those are called implicit functions, whereas before it was called an explicit function. All right? This is the last thing you should learn in terms of taking derivatives, because you need the chain rule, and the chain rule is typically the hardest thing to actually get good with. So let's get to it. The way you do this is you treat everything like a chain rule, right? So this is obviously a product rule, right? So we're going to have left is x, the right is y squared. Derivative of the left with respect to x, because we're differentiating with respect to x, is just 1 dx over dx, which cancels out. Then derivative of the right with respect to x is 2y dy dx. And then the right-hand side of the equation, you guys got this. Derivative of 1 is 0, right? So now we plug in our product rule. We get left derivative of the right plus right derivative of the left is just 1. And then it's an equation. So now we have a dy dx. Well, that's what we want, right? Let's do some algebra and let's get it, right? So we get 2xy dy dx equals negative y squared. Okay, now I divide by 2xy to isolate dy dx equals negative y over 2x. And whenever you're doing implicit, that's what you want. Here's a very valid question. Can we take higher order derivatives like the second under implicit differentiation? The answer is yes. And admittedly, it's a bit of a pain. Let's differentiate this with respect to x again, right? Of negative y over 2x. Well, there's going to be a quotient rule now, so it's an extra pain, right? We have low d high, which is going to be negative dy dx, right? Minus, in this case plus, because the negatives are going to cancel out, high d low over low squared. Okay. Well, we can simplify this, right? Divide everything by 2. That's going to be great. But we have a dy dx in our problem. What do we do now? I wish we had a value for dy dx, you know? Whenever you do a second or third order derivative under implicit, make sure you box, circle something, your original dy dx, and your answers from the nth derivatives, because you're going to use them for the higher order ones. So now we plug this into this, right? Negatives cancel out, x's cancel out. We just get y over 2 plus y over 2x squared, right? Which you multiply everything by 2 to make it nice again. You get, actually no, you can just do 3/2 y over 2x squared. And if I was a test grader, I would accept that, because I'd be like, a bit lazy, but I'll cut you slack this one time. If you want, you could just say 3/4 of y over x squared. But, sometimes you get lazy. So yeah, although I'm not going to focus on higher order derivatives with implicit, because it's not really focused on that much, especially in the test. it is very important to know. So yeah, with this example done, let's do another one. I've drawn a circle, right? The bonus points if you know the equation of a circle off your head. Let's say that this is just a unit circle, so radius 1. The equation is x squared plus y squared equals the radius squared. In this case, x squared plus y squared equals 1. Let's find the derivative of it, right? Differentiate with respect to x. Now, one thing to note, whenever I'm doing implicit, I don't write dx over dx and then cancel it out because I know it's going to cancel out, but I always write dy dx. The reason why I mentioned dy dx specifically, some people do y prime. It's right. It's not wrong at all. The issue is, if you get lazy and you forget this prime, it becomes a whole lot worse. Also, when you get to related rates and you get to trigger problems, you might have 3 variables and you don't, just writing the prime of it only shows you what your d top is and your d bottom, so what you're differentiating with respect to. So I always recommend just being less lazy and writing out dy dx. But you can tell where this is going. Or we can just divide by 2 first and then subtract. Y dy dx equals negative x. Dy dx equals negative x over y. Neat. Makes sense, right? Because at x equals 0, flat line, flat line. At y equals 0, doesn't exist, which means vertical lines. Okay, let's do another one. Here's a trickier one. E to the y squared sine x equals 2. Well, I'll give you a hint. The right-hand side comes out to 0. Okay, well, this is going to be a really nasty chain rule. But we know we're going to have e to the y squared sine x because the first one is e to the u and it doesn't change. Then we need du. So we said let u equal y squared sine x, right? Du, we have to differentiate this. Well, left is y squared, the right is sine of x, right? Derivative of the left is 2y dy dx. Derivative of the right is cosine of x. So now we just use our nice little formula, which is LDR, y squared cosine x, plus RDL, which is 2y sine x dy dx. So all of this has to now come up here. It's times y squared cosine x plus 2y sine x dy dx. And all of this is equal to 0, right? But hold on. Now we gotta get this, right? There's 2 ways of going about it. There's a trick way, which you can use in this case because it's a special case, but you should never really do this. This can never be 0, so you can divide by this, but I'm going to show you the other way of doing it, and you'll see that it should cancel out, right? So we're going to have to distribute all this. So we're going to have e to the y squared sine x, right, times y squared cosine x, y squared cosine of x, plus 2y e to the y squared sine x times sine x, dy dx equals 0, right? We're then going to subtract this one, move it over here to get 2y sine of x e to the y squared sine of x dy dx equals negative y squared cosine of x e to all that mumbo jumbo. Well, now you realize that you can just go noop and make your life easy, right? To get 2y, oh, I didn't even really write the sign here. Looks like SIK, that's kind of funny. We get 2y sine of x properly written, dy dx equals negative y squared cosine of x Whew. This is a lot of writing, man. Divide by this, we get dy dx equals negative y squared cosine of x over 2y sine x. But we're going to simplify. Negative sign stays, 1y cancels, so we get y over 2. What's cosine of x over sine of x? Cotangent of x. And this is our answer to dy dx. Whew, that is a lot of math. You are correct. This is one of those things that can and will easily get out of control, but you're not going to see this every other question, be it MCQ or FRQs. So while you do need to know it for the test, it is not the most important thing, because what they'll typically do is give you an easy one and say, hey, show that dy dx is this. Which, fun fact, that happened on this year, the 2025 AB FRQs on question 6A, which I will link at the end of the video. So stick around for that, because it was a hard FRQ. But yeah, let's move on to one more practice. All right, ln of x minus sine of y equals 3. You know the deal by now. We want to find dy dx. And this is the first time on the channel that I think I've posed some argument question. So I hope you know this, because I did go over it briefly. But let's do it. Well, what's the derivative of ln of u? 1 over u. So we're going to have 1 over x minus sine of y, right, times the derivative of the inside. Well, derivative of x is just 1 minus cosine of y dy dx. That's going to equal 0. Well, I'm going to give you a hint. Same thing as last time, but now there's no trick. We have to distribute. Well, 1 times this is just this. So we're going to have 1 over x minus sine of y, right, minus cosine of y dy dx over x minus sine of y equals 0. We're going to add this over. We get 1 over x minus sine of y equals cosine of y dy dx over x minus sine of y. Well, would you look at that? We have to multiply it by this, and that's the denominator here. So this all comes out to 1 equals cosine y dy dx divided by cosine. 1 over cosy of, cosy, good old cosy, equals dy dx. Well, 1 over cosine is secant. So you get secant of y equals dy dx. I chose this problem because it looks very nasty, but it's relatively common. It has a nice, clean answer. So yeah, that's implicit differentiation. If you're struggling on knowing what differentiation rule to use in what scenario, my best piece of advice is to practice implicit differentiation, because what you're doing is you're putting yourself on the hardest setting essentially. But if you can do implicit differentiation, you can do anything else in terms of differentiation. And this is at the heart of what is going to come later, which some people consider the hardest part of Calc 1, which is called related rates, which is just this with word problems, and optimization, which is the same thing, except you're then making sure it's the best of what you can do given the conditions. So if you can really get this down, you're going to be in a lot better standing than the average Calc 1 student. So I do recommend you look at the free book in the description below, and you just go to the chapter, I think it's like chapter 3 that has implicit differentiation. Look at it and just look at the problems, hit them hard. They do have answers in the back of the book, I believe. So do that practice and it'll do you great. But regardless of whether you do or don't, I want to say thank you for watching. As always, I do mean it. And if this was useful, because it admittedly did throw me off back when I was first learning Calc 1, but I persevered and now look where I'm at. But if you found this helpful, consider leaving a like. If you have any feedback or tips leave a comment and I'll read them. I try to read all the comments. And then if I was really, really helpful, you could consider subscribing. And yeah, as always, thank you for watching. Have a good day.